Hi, this is the course BMI 5750, Methods in Biomedical Informatics and Data Science. Today I'm going to give you a brief overview of biostatistics. This is part 1. The learning objectives of this class. First, we will talk about some important and basic statistical concepts. Second, we will cover basic probability principles and concepts. Third, its base rule and its applications. Fourth, we will talk about sensitivity and specificity and give you some examples in real clinical applications. So at first, we need to think about what's statistics and why do we need statistics. So here is a basic paradigm of statistics. We have population of people that we want to study, for example, group patients. Sometimes population is quite large, so we cannot study each and every one of them. Usually people pull out the sample of them. That is a proportion of the population that we are interested in. Usually there are some parameters measure the characteristics of the population. Those parameters are usually unknown. However, for the samples that we pull out from a population, we can summarize some statistics from them, and those statistics are known. Then we use the statistics that we generated from sample to derive statistical inference about the parameters. Now let's talk about the comparison between population and sample. We want to draw some conclusion about population parameters using the information contained in a sample of observations. Because it's impossible to collect data on the entire population, which is usually quite large. So there are some examples. Example 1, we can ask question, is the blood pressure of the treated patient group lower than the untreated patient group? Example 2, that's people usually ask this kind of question in genomic analysis. Is the mean expression of a gene similar between different groups, for example, cancer tissue and normal tissue? And usually the gene expression is measured by mRNA abundance. So these are two examples that we usually see in our everyday research and also in our clinical practice. Parameters versus statistic. So parameters is a value derived using the information of everyone in a population. Usually it's fixed but unknown. For example, the mean age of the population or the proportion of females in the population. However, we can use statistics that we generated from a sample to derive information for a population. So a value calculated from the sample information is called a statistic. Statistic is known but varies from sample to sample. For example, we get sample mean of a group of people or the sample proportion of females. A statistic is used to estimate the parameter. Since we talked about sample, then we need to talk about sampling distribution. Say we have a population. The mean age of the population is 50, and the standard deviation of their age is 5. The population is quite large, and we cannot study each and every one of them, so we pull multiple samples of the same size from this population. For example, each time we sample 1,000 people from this large population. On this slide, we show that we generated 6 different samples. For each of the sample, we have the same sample size. That's to say we have 1,000 people in one sample. However, we do not usually extract the same people from the population. So these 1,000 people in the 6 different samples are not exactly the same. For sample 1, the mean age is 44, and the standard deviation of age is 4.1. For sample 2, the mean age is 55, and the standard deviation of age is 3.2. So you can see these values are different. That means there is variation in the mean and the standard deviation of the samples that we pull out from the population. So what's the sampling distribution? if we were to continue drawing samples indefinitely, we select all possible samples of size n. Here, n equals to 1,000, that's 1,000 people from the population, and we compute their means. For sample 1, the mean age is x1 bar, and for sample 2, the mean age is x2 bar, and for sample n, the mean age is xn bar. We calculate means for each of the sample. Then we get the sampling distribution of all the means, that's x bar. X bar is the sampling distribution of means of all samples of size n. In practice, we do not select all possible samples of size n from a given population. Understanding properly of the theoretical distribution of their means allows us to make inference based on a single sample of size n. So here is a simulation of sampling distribution of mean. For example, we generate 1,000 samples by rolling a die n times. Here we set value of n equals to 1, 5, 10, and 40 respectively. Then we show the histogram of the resulting 1,000 sample means. So for example here, this figure shows 1,000 samples. In each of the sample, we roll the die 5 times. And this figure shows the value of the die that we see, because the value of the die range from 1 to 6. There are 6 possible values. Then this figure shows the probability of each number of die appears. This is related to the famous central limit theorem. Central limit theorem says, for large sample size, the sampling distribution of the sample mean is normally distributed, regardless of the distribution of the original data. The mean of the sampling distribution is identical to the population mean. However, the standard deviation of the distribution of sample mean is equal to the population standard deviation divided by the square root of n. This is known as the standard error of the mean. So we write it like this. The variable x bar follows a normal distribution with a mean, mu, and a standard error. Here we show a plot of sampling distribution of the means with different size n. Now we increase the sample size from 1 to 20, and we generate samples much more times than 1,000. Then we can see that the larger the sample size is, the narrower the distribution is. The mean is still here equals to population mean. However, standard deviation equals to this. So the larger the sample size, the smaller the standard deviation is. Here are some probability of sample estimates. First, bias. The second is variability. Bias occurs if values of sample statistic consistently overestimate or underestimate the population parameter in repeated samples. Variability describes the dispersion of the values of the sample statistic in repeated sampling. Now we show the difference between the two concepts with a figure. Say this rectangle is the whole population, and we draw a sample from the population that contains 10 sample points. And the first figure here shows low bias, low variance. Low bias means that the expected mean of this 10 sample point is still very close to the true mean of the population. The second figure on the right-hand side shows high bias because the mean of the sample here in the right corner, it is really far away from the true population mean. So that's high bias. However, since all the sample points are close to each other, the variance is low. And the third figure in the bottom shows low bias because the mean of the 10 sample point is still very close to the real population mean. However, Since the sample points are far away from each other, there is high variance in the sample. So this figure shows the difference between bias and variability. One very important point is we need to distinguish the measurement error versus natural variability. One example of the measurement error is when we measure a large distance with a ruler. So the measurement that we got from the ruler is not always the same. That's the measurement error. And also there is another concept called natural variability. One example is the blood pressure that we measured from one time to another. So there's natural variability there. The key point is that we need to sort out difference due to natural variability from difference due to features that we define, measure, and possibly manipulate. A biased measurement differs from an unreliable measurement because it is consistently off the mark in the same direction. So how do we describe a sample? There are different data types. For example, continuous, discrete, or ordinal categorical. There are also different summary statistics we use to characterize the sample. For example, mean, standard deviation, variance, range. So these are all descriptive statistics, so we have no assumptions or worries about sampling method. Graphs is a very good way to summarize and display data. Here is a bar chart. We usually use that for nominal and ordinal data. Histogram, it is a very good way to show the frequency distribution for discrete or continuous data. And here in the bottom, that's box plot. There are 5 useful numbers for a box plot. Minimum is the minimum value of all the sample points. Maximum is the maximum value of all the sample points. It also shows the first quartile, the third quartile, median, and also IQR, which is interquartile range. So we usually use box plot to show the comparison between different samples or different groups. So here, for example, we show the age of the male group and the age of the female group. We also use graphs to depict relationships. For example, here is a two-way scatter plot. It shows the relationship between FEF and length. There is a line graph here. Note that an association does not always imply a cause effect. Outliers. Outliers are values that are far from the bulk of the data. They distort the mean and standard deviation, but usually do not have effect on the median and IQR. So actually here, in the box plot, we can see the outliers labeled here. There are 2 reasons for an outlier. It is a legitimate data point and represents natural variation. So in this case, do not delete them. So we usually need more data in that range. The other reason might be mistake. So mistake was made when recording the measurement. It can be deleted in this case, but we need to know the reasons for the mistakes, and we need to report it. Maybe you have heard the statement that the mean plus or minus 2 standard deviations encompasses most of the data. Is this true? Actually, it is true. For most of the case, it is called the empirical rule. If the data is symmetric and unimodal, we can say that approximately 68% of the observations lie in the interval centered at mean and around plus or minus 1 standard deviation. 95% of observations lie in the interval mean plus or minus 2 standard deviations, and 99.7% of the observations lie in the interval mean plus or minus 3 standard deviations. This is a figure showing the empirical rule. So this is a mean, and this is the range minus 1 or plus 1 standard deviation. 68% of data lie in this range. There's another important rule is Chebyshev's inequality. This inequality is true no matter the shape of the data. For k greater than 1, at least this number of the data lie within k standard deviations. For example, if k equals to 2, then 75% of the values lie within 2 standard deviations of the mean. Now we have a discussion question. Does using plus or minus 2 standard deviation always make sense? We will leave this question for online forum discussion, so please feel free to leave your message and your answers on the forum. So we will discuss about it, and then I will tell you my answer. Now we move on to the basic concept of probability. We need to think about why do we need to know probability theory. Say we assume we know the population that give rise to our data, and then we ask, what is the probability of an event? We need to know how the information contained in the sample can be used to infer the characteristics of a population from which it was drawn. It provides a means of quantifying uncertainty. There are several probability rules. The first rule is if there are only 2 possible outcomes, then their probability must add to 1. For example, if we toss a coin, there are only 2 possible outcomes, heads and tails. So, the probability of a coin get heads or get tails sum up to 1. The second rule is if 2 outcomes cannot happen simultaneously, they are said to be mutually exclusive. We still take the example of tossing a coin. So, because the coin can either be heads or tails, it cannot be heads and tails at the same time. So, these 2 outcomes are mutually exclusive. The third rule is if 2 events do not influence each other, and if knowledge about one doesn't help with the probability of the other, the events are independent. For example, if we have 2 coins, we toss one coin, it gets heads or tails, and then we toss the second coin, it gets heads or tails. So heads or tails of the 2 coins are independent. Whether we got heads on the first coin doesn't influence whether we get heads on the second coin. Venn diagram is a very good way for people to depict probability. We usually use this figure to show the intersection between 2 events. Say you have 2 events, A and B, and the intersection between A and B are shaded. On this figure, we also shade A and B together to show the union of the 2 events. The complement of an event is denoted as A superscript C. Say this is all the events with probability equals to 1, and the complement of event A is all the area outside A. That's A superscript C. Now explain probability in a frequentist definition. If an experiment is repeated n times under essentially identical conditions, and if the event A occurs n times, then as n grows large, the ratio m divided by n approaches a fixed limit that is the probability of A. For example, we toss a coin 1,000 times. So each time we are under essentially identical conditions. And the event A, for example heads, occurs m times. Then, as n grows large, for example, it grows from 1,000 to infinity, the ratio m divided by n, that is the number of heads, the number of times the coin gets heads, divided by the total times that we toss this coin, it approaches fixed limit, that is the probability of A. And this probability of A, it is the relative frequency of occurrence. This number is between 0 and 1. PA superscript C is the probability of complement of A. And the union of A and AC has the probability equals to 1. That means the relative frequency of heads plus the relative frequency of tails equals to 1. We use the upside down U to represent the intersection between A and A complement, because A and A complement have no overlap, so the probability of A and A complement intersection equals to 0. That's to say, A and A complement are mutually exclusive. This is a figure showing the sample probability of heads. The x-axis is the trial number. It's the number of trials that we toss this coin. And when we toss the coin from 1 time to 100 times, we can calculate the probability of getting heads. If the coin is a fair coin, when the trial number increases, we can see the probability of getting heads approaching 0.5. Maybe this coin we are tossing is not a fair coin though. The law of large numbers says that if you perform the same experiment a large number of times, for example, you toss the same coin a large number of times, the average result will converge to the expected value. In the previous example, the sampling proportion of heads will converge to 0.5 if the coin is a fair coin. We need to avoid the gambler's ruin. Suppose you have generated a sequence of 10 straight heads. What is the probability that you get tails on the next flip? Is it greater than 1/2? Let's think about it and have a discussion in the forum. We learn a lesson from this. Even though in the long run things average out, that does not change the probability of the next outcome. Now let's talk about probability operations. The first operation is additive rule of probability. If A and B, the two events, are mutually exclusive, for example, we get heads or tails when we toss a coin. Getting heads and getting tails are mutually exclusive, so probability A plus probability B, they sum up to probability of A union B. If A and B are not mutually exclusive, then the probability of A union B is not equal to probability A plus probability B. We need to minus the probability of A intersection with B. That is the probability of A plus probability of B minus the probability of intersection A and B. Another operation is multiplicative rule of probability. And here, probability B given A is called conditional probability. Or we say it is the probability of B given A has already occurred. That's conditional probability. Conditional probability, we can also write it like this. PB given A equals to the probability of A intersection with B divided by the probability of A. Actually, you can see that it is the same form of this. We just write a multiplicative rule in another format. And also we get probability of A given B equals to the probability of A intersect B divided by probability B. Both of the two conditional probabilities are true, given the denominators probability A and probability B are not equal to 0. When the outcome of one event has no effect on the occurrence of the other, the events are independent. If A and B, these two events, are independent, we write them as PB given A equals to PB, and PA given B equals to PA. That's probability A intersection with B equals to probability A multiplies probability B. We want to ask you a question. Can a pair of events be simultaneously mutually exclusive and independent? Let's have a discussion. Please leave your message in the discussion forum. Now let's move on to law of total probability. Let's define A1 to AK are mutually exclusive events. Then PB is summation of a conditional probability of B given AI multiplies the probability of AI. We can write it in another form, which is the summation of probability B intersection with AI. That's because probability B intersection AI equals to probability B given AI multiplies probability AI. This came from the multiplicative rule of probability. Here, for example, say we have K equals to 4. Then we have 4 mutually exclusive events, A1, A2, A3, A4. And we show it in this figure. A1, 2, 3, 4, they have no overlap, and they are 4 mutually exclusive events. And based on the law of total probability, we can write it in the form of PB equals to the summation of this. We can write PB equals to this. And for each component of PB given AI multiplies PAI, we can write it in the form of probability B intersection AI. Here is an example. John's final grade of this course is 4 possible outcomes, either superb, very good, so-so, or complicated. These grades are mutually exclusive. Then we define the events A1 to A4 as John getting a grade of superb, very good, so-so, or complicated. We define B as the event of John passing the course. And what's PB? PB equals to the probability of A1 and B happen together plus A2 and B happen together plus A3 and B happen together plus A4 and B happen together. Then we can write out the formula based on law of total probability. What is 1 minus PB? Actually, that's the probability of the event John failed the course. Now let me give you a definition of sample space. The set of all possible outcomes of a particular experiment is called sample space for the experiment. For example, if the experiment consists of tossing a coin, the sample space contains 2 outcomes, heads and tails. Since we have this definition, I want to introduce Bayes' theorem. Let A1 to AJ be a finite partition of the sample space, and let B be any set. Then for each I equals to 1, 2 to j, we have the conditional probability PAI given B equals to this. Actually, this part equals to the probability of B intersection AI. And PB equals to this because of law of total probability. There are many applications of Bayes' rule in our real life. So here is an example of diagnostic test. As an application of Bayes' theorem, let's consider a diagnostic test. Here we want to calculate probability you have a disease given the test is positive. This is called the positive predictive value of the test. Let's review some notations and general definitions. We have a population of people, and these people took a diagnostic test. The test result can be either positive or negative. And these people are either with disease or without disease. Then we can generate this two-way table. The number of people with disease and the test result is positive is true positive. The number of people without disease but the test result is positive is called false positive. The number of people with disease but the test result is negative is called false negative. The number of people without disease and the test result is negative is called true negative. So using these TP, FP, FN, and TN values, we can calculate several statistics: sensitivity and specificity. Sensitivity is the probability of a positive test result given that the individual tested actually has the disease. Sensitivity measures the ability of the test to identify those who have disease. On the other hand, specificity is the probability that a test result is negative given that the individual tested does not have the disease. Specificity measures the ability of a test to exclude those who don't have disease. And sensitivity and specificity, the most relevant for population health perspective. Predictive value. Positive predictive value is the probability that you have the disease given that a test result is positive. On the other hand, negative predictive value is the probability that you do not have the disease given that the test result is negative. And these two values are most relevant for patient perspective. Assuming a random sample, when we have disease condition yes or no, and we have test result yes or no, positive or negative, we calculate these four values, TP, FP, FN, TN, and use this, we can calculate sensitivity, specificity, and also predictive values. We use these as the measures of the association between disease and test results. Here is an application of Bayes' rule. This example came from diagnostic testing. It relates the predictive value of a test to its sensitivity and specificity, as well as to the prevalence of the disease in the population. For example, we have TB or chest X-ray test data. It's shown here in this table, and we want to ask, what is the probability that a randomly selected individual has TB given that this person's X-ray is positive? That is, we want to ask, what is probability of disease given the test result is positive? This is the steps. The first step, we want to calculate what's the probability that an individual in the general population has TB. In a dataset, 1,820 subjects were not chosen at random. Thus, we don't know the prevalence of the disease. However, we know that in 1987, there were 9.3 cases of TB per 100,000 subjects. So we get probability of disease equals to this. The second step, we want to calculate what is probability that an individual does not have TB. This value equals to 1 minus PD. The third value we want to calculate is what's the probability of a positive X-ray given that an individual has TB. This is the sensitivity of the test. So actually we can calculate sensitivity from the two-way table. The fourth value we want to calculate is the probability of a positive X-ray given that a person does not have TB. This value is the complement of the specificity. We can also calculate it from the two-way table. And now we have four values, and those four values calculated above, we can use them to calculate the final result. And here we derive this result from Bayes' rule. And here we summarize all the calculations in one slide for your reference. And the final result is this. Now let's summarize the TB example. Before an X-ray is taken, a randomly selected subject from the US has a 0.0093% chance of having TB. This is called prior probability. After an X-ray, if the result is positive, the same individual has a 0.239% chance of having the disease. This is called posterior probability. The posterior probability takes into account a new piece of information which came from positive test result. We divide prior probability by posterior probability. It equals to 25.7. This means that the probability that an individual with positive X-ray has TB is 25.7 times of the probability for a person randomly selected from the population. This is the end of this class, and next class we will continue biostatistics review. And for your reference, you can read Chapter 1 from the book Statistical Inference.